In this video, we're going to look at exponential equations. So your learning target for today is to deepen your understanding and generalize the roles of the y-intercept and the multiplier in exponential equations. So in integrated math 1A, you looked at multiple representations, which means a table, a graph, an equation, or a situation of linear functions. This chapter, you're going to use multiple representations to learn more about the multiplier and the y-intercept of exponential functions. And so let's look at some vocabulary. What we're going to be dealing with today and in this chapter actually are geometric sequences. So a geometric sequence is a sequence that is generated by a multiplier. This means that each term of a geometric sequence can be found by multiplying the previous term by a constant. Here's an example. What is the multiplier here? 5 times what gives me 15? 3. And we need to make sure it's constant throughout all the terms. 5 times 3 does give me 45. So this is a geometric sequence, and this is an exponential. Okay, and so that's what we're dealing with in this chapter. As a review, an arithmetic sequence, each of the terms of an arithmetic sequence can be found by adding the previous term by a constant. Where have you learned arithmetic sequences? In integrated math 1A, and a linear line, a linear equation is an arithmetic sequence because you are adding the same constant each time. So if I'm looking at like an example here, 0, 1, 2, 3, if I had 5 here and I went to 15, I would actually be adding 10. 15 plus 10 is 25, plus 10 is 35. Okay, so an exponential is a geometric sequence where you're multiplying each term by a constant. Whereas linear lines, they were arithmetic sequences because you added something to each constant. As a quick review of an exponential equation, and it's quick because you actually had an introduction to exponential functions in chapter 5 of Math 1A. But to review it, make sure we're all on the same page. A is your starting value. It's your y-intercept. It's your initial value. It's what you start with. B is your multiplier. It's what are you doing to each term? What are you multiplying it by each term? And then X and Y would be your defined variables. And occasionally when students are asked to define their variables, they will also try to include and tell me what A and B are, which is the multiplier and starting value. But A and B are not, they're not variables. Only X and Y are. So it's very important that you understand exponentials. It's not hard, I promise. You have your y-intercept, your starting value. What do you do to it each time? Your multiplier to the x, as long as x is 0. Okay, so if you need to write that down in your notes, do it. Otherwise, let's move on. So let's look at some of the connections between the multiple representations of an exponential function. Okay, so here we have a word problem. A major technology company, Exponential, is growing incredibly fast. The latest prospectus, which is a report on the company, said that so far the number of employees, Y, can be modeled with the equation Y is equal to 3 times 4 to the X, where X represents the number of years since the company was founded. How many people founded the company? How can the growth of this company be described? How many people founded the company? That's asking for your initial value. How many people started the company? What is the growth? That is your multiplier. And these are so easy to find in an exponential function. Because on the previous slide and in your notes, you know that 3 is the initial value. And you know that 4 is your multiplier. And so how many people founded the company? 3 people founded the company. And how can the growth of this company be described? Well, it looks like it's quadrupling. It's growing by a factor of 4 each time, right? I don't know how to spell quadruple. I think like that. But it's quadrupling every time. It's multiplying by 4. Is it every year? Or the number? Yes, number of years. Okay, so very simple. We took a confusing looking word problem, decoded it. We know that 3 is the initial value, the starting value. 4 is your multiplier. What are you doing to the term each time? You're multiplying it by 4. However, as part of a major scandal, it was discovered that several statements in the company's prospectus were false. If the company actually had 5 founders and doubles in size each year, what equation should have been printed in its report? So we know that our equation is y is equal to ab to the x, where a is the starting value and b is the multiplier. So very, very simple. How many people started the company? They had 5 founders. So I'm going to have y is equal to 5 because that's my starting value. And then what happens to it each year? It doubles. It's being multiplied by 2. And then to the x power. Okay, that's how simple exponentials can be. What did it start with, and what is its multiplier? Let's try our next example. Example 2. So Arnold dropped a ball during the bouncing ball activity and recorded its height in a table. Part of his table is shown at right. What was the rebound ratio of his ball? Right there, it's asking for growth. Right there, it's asking for the multiplier. Okay. And then from what height did he drop the ball? What do you think he's asking for? He's asking for the initial value. He's asking for what is y, when x is 0. It's asking for this number right here. So how can we figure out that number? Well, first, it helps us immensely to figure out what the multiplier is. This is really important to figure out what you're multiplying each term by. These are the steps. You take one of your numbers, this one, it doesn't matter, and divide it by the number on top. Because since you're multiplying going down, what's the opposite of multiply? Divide. And so if you take this number and work backwards by dividing, you can figure out what your multiplier is. So I'm going to put 67.6 divided by 84.5 in my calculator right now. And you should try the same. And I get 0.8. So the multiplier is 0.8. Okay. Every single term in this situation is being multiplied by 0.8 to get the next term. And so we now know what the initial value is. And again, our equation is y is equal to ab to the x, where a is the initial value and b is the multiplier. So we now know the multiplier is 0.8. So we can plug that in. But we still need to figure out what a is. And so coming back to our table, if going downwards, we're multiplying by 8. To go backwards, let's see, 54.1, you are dividing by 0.8. Okay, and you can test it yourself in your calculator. 54.1 divided by 0.8 gives you approximately 67.6. And so let's figure out going backwards. Let's do 84.5 divided by 0.8, and you get approximately 105.6. And we need our initial value, right? So I'm going to divide that number by 0.8. 105.6 divided by 0.8 is 132. How beautiful. Okay, so that is our A value. I'm going to plug that in here, 132, and here is my equation. So as a quick review, to figure out your multiplier, to figure out this number, you took one of these numbers and divided it by the number on top to get the 0.8, and that is your multiplier. Then, since going down, you're multiplying by 0.8 each time. To go backwards, you have to do the opposite, which is divide. And that's how I got these numbers up here. 84.5 divided by 0.8, and my calculator gave me approximately that. 105.6 divided by 0.8 in my calculator gave me approximately that. That is my initial value, and that's why I plug it in for A in that spot. Moving on to, the third and final word problem. So let's look at another connection, okay? Let's look at this example. A computer virus is affecting the technology center in such a way that each day a certain portion of virus-free computers is infected. The number of virus-free computers is recorded in the table at right. So how many computers are in the technology center? It's asking for how many did we originally start with, and that's 27. And we know that because when X is 0, that is our initial value. What portion of virus-free computers is infected each day? That's asking kind of about a multiplier. It has to do with a multiplier. So now that you know from the previous slide or previous problem, how can we figure out what the multiplier is? Well, you can take one of the numbers, one of the terms, divide it by the one on top. And if I do 18 divided by 27, I get 0.6666666 forever, which is 2/3. So my multiplier is 2/3. And I want to make sure, so if I multiply by 2/3 again, I should get 12, and I do. Now here's the tricky part. 2/3 is the multiplier, but it's asking for what portion of them is infected each day. This multiplier is telling you how many are uninfected, but it wants to know how much is actually infected. So this one threw a little curveball. How do we figure out how much is actually infected? Well, if 2/3 are being uninfected, 1 minus 2/3 is, you've just got 1/3. So 1/3 of the computers are being infected each day, which can be confusing because this is talking about uninfected. So 2/3 of them are uninfected, which means 1/3 is infected. And how many computers will remain virus-free at the end of the third day? We can figure that out easily because our multiplier is 2/3. So to go to the third day, I'm going to multiply by 2/3 again, and 12 times 2 divided by 3 is 8. Okay. So 8 computers will remain virus-free. And let's see. So let's go ahead and have one final example. Let's create a table and a graph given this equation. Easy peasy. We know that 2 is our initial value. So I'm going to put a point at 2. I also know 3 is my multiplier. I'll put y-intercept is our multiplier. So if I start at 2, 2 times 3 is going to give me 6. Okay, and I can start our table here. When x is 0, we started at 2. When x is 1, our multiplier is 3. So 2 times 3 is 6. When x is 2, I'm going to multiply it by 3. 6 times 3 is 18. When I go to 3 times 18, it's going to keep going, right? And it's already going to be way off of our graph. And so when x is 2, it's at 18, somewhere way up here. So a quick sketch. Oh my gosh. Okay, it's difficult on my tablet, so you got to give me some, oh no, grace on that. Okay, but that's a sketch of y is equal to 2 times x to the x power, 2 times 3 to the x power. And here's our table by plugging in x values and doing the math, and then by creating a graph. So that is it for this video. Thank you.